Okay, section 10.2, we are looking at pressure, particularly air pressure, and what it is, how we measure it. So what air pressure is, we can think of it this way. Well, we can think about it this way. This is what it is. Air pressure is the air that is pushing down on top of our heads. So there's gas molecules in our atmosphere. Those gas molecules are being pulled down by gravity. Even though they're very small, we don't think of it as a huge force, but there's enough of them, and if we measure all the way up to the top of our atmosphere, and obviously as we go up, our atmosphere gets thinner and thinner and thinner, so there's less and less gas molecules, but if we take that whole chunk that's above our heads, and we look at the gravitational force pulling down on those gas molecules onto our head, well, that is what we'd call, what we'd call air pressure. And notice it has a value here for air pressure in this nice little graph. It says if we have 1 square meter, okay, so a meter by a meter, which, well, is bigger than the surface of my head, but 1 square meter would have a mass of 10 to the 4th kilograms. Holy smokes! So 10 times itself 4 times. So that's 10, 1, 2, 3 zeros on top of it. So that's a lot of mass, 10,000 kilograms. But obviously we don't recognize it because we've always had that pressure pushing down upon us. So if we're down at sea level, notice, we have a lot of gas molecules pulling down on us. We have this whole column of air that gravity is affecting on pulling down. And notice what this is supposed to indicate is, notice as we go up in altitude, as we climb up Mount Everest, the density of that gas decreases. So also the pressure decreases quite a bit. Notice at sea level, our standard pressure is 101 kilopascals. So you'll notice different units than we were talking about over here. They were talking about atmospheres and kilograms. Now we're talking about kilopascals. At Mount Everest, the pressure is 31 kilopascals. So there's significantly less air pressure because, two reasons. One, the density of the gas decreases quite a bit as we go up, but also if you're standing on Mount Everest, there is a much smaller column of gas being pulled down by gravity than right here. So you want to think about yourself with a big column of air pulling down on your head. And after you exit the atmosphere, well, then there's a 0 kilopascals of atmospheric pressure. So here's another graph to indicate this. Just like graphs. So station A, this is right at sea level. Obviously we can go below sea level, and if you went below sea level, say in Death Valley, which is below sea level, well then you should have a higher atmospheric pressure because again there's more atmosphere pulling down on your head. But in this one, as we walk up, so we're gonna get ready, we have our little walking stick here. Maybe we're gonna double walking sticks when we walk up, well the pressure decreases. And you feel this when you drive up and down a big hill. You'll feel the pressure change and you'll have to pop your ears, just like in this one where you have an airplane. Notice as the airplane goes up, the pressure, the cabin has to be pressurized, but even though it's pressurized, the pressure inside the plane still decreases, and so your ears still do pop. And then sometimes, especially if you're traveling with little children and it's flying down, well then the pressure increases quite dramatically and can really hurt, especially if you don't know how to pop your ears, which is a skill you have to learn. You don't know that as a baby. Okay, so we're still going up the hill. Notice at station B, we have 915 millibars. Notice we have yet another unit for measuring pressure in. Again, there's a smaller column of gas above us, right? And so the pressure decreases. Notice what's also happening to our temperature. Our temperature is going down. That's another thing we'll talk about, why we have less pressure as we go up in altitude typically as well. Or less temperature, I should say. Now we go up to station C. Again, that column is even smaller. The pressure goes down even more. Now, if trying to figure this out, think about it similarly to diving in a swimming pool. So this is me. I should put some shorts on myself. Some nice swimming shorts. This is me diving down into a pool. As I dive down into that pool, what I will feel is if I dive down to the bottom, now I feel a lot of pressure, a lot of weight pushing down on me, a lot of water pressure, and that is because there's more water on top of me. So at your sea level, there's more air on top of you, there's more air pressure. If you dive down to the bottom of the pool, you can feel it starting to kind of push down on your body and gets a little uncomfortable if you dive down far enough because that column of water just gets heavier and heavier. Obviously, there's limits to how far people can dive down into water before it actually crushes them because of the weight. You couldn't go to the bottom of the sea or the ocean, we all know, because the water pressure would crush you because there'd be such a high column of water on top of your head. And it's also wreaks problems with the dissolved gases in your blood as well, even at much lower depths. Okay, So now, what we have is we want to know how we measure pressure. Well, typically, or I should say, traditionally, pressure was measured, and this is why our units are in mercury. Pressure was generally measured with mercury. Mercury is nice because it's a liquid, and it expands very uniformly with effects of temperature. So it was easy to get mercury. We'd fill up this tube. People would fill up a tube. Notice it's closed on the side. And they'd flip it over into a pool of mercury. Doesn't that sound great? And what they would see is that this liquid level would not just run out of the tube. It would not just run out of the tube. So gravity's acting down on it. Even though it's in a tube, there's still the force of gravity. But the atmospheric pressure pushing down on the surface of the mercury held the liquid up in the tube to a certain height. Now, it didn't keep it full, right? But held it up to a certain height. And that height at what we'd call standard pressure is 760 millimeters of mercury. So it's actually a length measurement. If you measured from here to here, 760 millimeters of mercury. Now, this worked very, very nice because this is 760 millimeters. So they could have a tube maybe about a meter high, and they could have a nice barometer, a nice thin little glass tube on the side of their lab, and they could measure the changes in atmospheric pressure. Because when we have weather systems, that atmospheric pressure does change. Typically, cold weather fronts have higher pressure. We have warmer air fronts that tend to have low pressure. They're low pressure cells, so high pressure, low pressure cells that you see on the news are actually high and low pressure cells, and they're changing the atmospheric pressure because of the temperature of the gases and such in the atmosphere. So again, the atmospheric pressure would keep the mercury up in this tube to a height of about 760 millimeters of mercury at standard conditions, again, at sea level. And again, when it would change. Now, you'd think, well, why use mercury? Because mercury is not super terribly easy to get. We also know now that it's a bit toxic, and so we might not want mercury, even though it'd be really nice to have a mercury barometer like this. Why wouldn't they use, say, water? Well, mercury is much more dense than water, and so it's much, I hate to use the word heavier, but I will say heavier. So the air pressure can't keep mercury up into a tube as high as, say, could keep water. Now, we could also build a water barometer, and we could put water in a cup, and we could fill a tube with water, and we could flip it around in the cup. But the problem is water is so much less dense than mercury that the column of water would be much, much higher, almost upwards of like 30 feet. Now, that wouldn't be very easy to have in your lab. Now, as you've noticed, we have a lot of different units. We were talking about millimeters of mercury because originally pressure was measured in mercury because mercury is a nice dense liquid they could use, have a nice lab side setup there. We also saw that, notice, it's also in inches of mercury if we want to use the English system. We have millibars here. On this one we had kilopascals. In this one, they're talking about atmospheres. So originally, there was a lot of chemistry going on with gases, and so that's why we have so many different units of gases. There's experiments going on in different places. They had different ways of measuring, and so we have different units. So we're going to have to convert between all of these. Our standard is atmospheres. Okay, ATM is atmospheres, and our standard pressure at sea level is 1 atmosphere. So that's the units we'll want to use most often. Occasionally they'll give us values in other values, so millimeters of mercury. Notice to convert that into atmospheres, 1 atmosphere is equal to 760 millimeters of mercury. So we'll need to use some conversion units. I'm not going to expect you to remember all the different conversion units, but I will expect that you can use them. Notice kilopascals is 101.325. Pascals is 100,000, 1,325. Notice it's just a kilopascal or a pascal by itself. And look at bar. Notice a similar number, 1.031 is our conversions to bar, or like in that other one used, millibar. So we have some conversions to do. Before we do any conversions, let's take a moment to look at something in your book. We do typically want to do any calculations we have in standard temperatures and pressures. STP, as what it's called, which is standard temperature and pressure, typically 1 atmosphere and 0 degrees Celsius. That's what we use to call standard temperature and pressure. So let's do just a couple conversions. So we have kilopascals. Kilopascals, we have 151.9 kilopascals, and we want to convert all of these into atmospheres. So I'm going to go back and look at that chart I had, and it says the relation between kilopascals and atmospheres is that 1 atmosphere is equal to 101.325 kilopascals. So that's the number I'm going to bring. So I'm going to just use this as a conversion factor. It's always 1 atmosphere with these. So 1 atmosphere, which is icicles on top, is 101.325 kPa, kilopascals, and there's my conversion. I have it set up. Let's do torr. Torr's kind of a fun one. 456 torr. Now that we haven't looked at yet. We haven't looked at what torr is. Well, torr is equal to, we could just change this because torr is equal to millimeters of mercury. Isn't it fun having all these different units? So if we know the conversion for millimeters of mercury, we know the conversion for torr. So I'm going to say 456 millimeters of mercury, and if I go back again and look at that chart, what I said was the relation was 1 atmosphere is 760. Those are the values that are here on this chart. So again, 1 atmosphere on top divided by 760 millimeters of mercury, and that will give me my answer in millimeters of mercury, or again, same thing as torr. Last one, what else do we have here? 1 in millimeters of mercury. So we'll use the same conversion unit, 912 millimeters of mercury. This time I don't have to convert it from torr because it's already in millimeters of mercury, divided by 760, and we are done because that is 1 atmosphere. And I'm not going to plug them through. You can do that on your own calculator. Have some fun.